Today we're going to look at radioactive decay. We're going to study the three types of particle emitted from radioactive nuclei and some of the properties of those three types of radiation. So here we go. Okay, nuclei come in two types. Some are stable and they will remain that way forever, but others, the great majority actually, are unstable. And many of these nuclei will decay into different nuclei by the emission of energy in some form. And they're unstable because the balance between the protons and neutrons, often the number of neutrons compared to the number of protons, or something about the energy balance between them needs fixing in order for the nuclei to settle down into a stable state. And in doing so, these nuclei will emit either a particle or a photon in order to lose some of that energy. And I'm sure you're very familiar with the names of the three particles. Okay, we have what we call alpha radiation, beta radiation, and gamma radiation. Now, alpha and beta radiation are particles, which we'll look at later on. Okay, gamma radiation is a photon of electromagnetic radiation, just like the gamma in the electromagnetic spectrum. You know, X-rays, gamma rays right at the top of the electromagnetic spectrum. It's the same stuff. In this case, it's what we term a photon of gamma radiation. Okay, so before we go into all that, a little bit of history. This guy here is Antoine-Henri Becquerel. He was a French physicist, and he was the first person to realize that some substances emitted some form of radiation. He did it with uranium salts and purely discovered it by accident. Marie Curie, who I'm sure you've definitely heard of, was a student of Becquerel's, and along with her husband Pierre, they isolated radium, which is an element, and they named radium after the rays or the radiation that it was emitting. And they also studied polonium, which is another radioactive, or certain isotopes of polonium are radioactive, and they also studied that and named that after their native, or Marie's native, Poland. Ernest Rutherford is sometimes called the father of radioactivity. Not only did he discover the nucleus of the atom, but he was also the first one to realize that there were three types of radiation, alpha, beta, and gamma, and discovered some of the properties of those three. So there's some of the big players in this topic. Okay. All right, so alpha decay. Alpha decay it comes about because of an interplay between the strong nuclear force and the electromagnetic force. Now, if you remember, the strong nuclear force is the one that holds nuclei together, and the electromagnetic force, particularly the electrostatic force, is the one that's responsible for the repulsion of charged particles. In certain larger, particularly larger, radioactive nuclei, the ratio of these two nucleons, the neutrons and the protons, isn't quite in balance. So that rather than the strong force being able to hold the nucleus together, because obviously it leaks out around the nucleons a little bit, the nucleus gets so large that this force can't hold the nucleus together, and the electrostatic force becomes very important. And when this happens in certain nuclei, it will settle down and emit a little bit of that excess energy by getting rid of what we call an alpha particle. Now, an alpha particle is simply a cluster of two protons and two neutrons in a tiny little ball like that. And because of this, it's equivalent to a helium-4 nucleus, effectively a double ionized helium-4 atom. But obviously the electrons were never there in the first place. It's just the same thing as a helium-4 nucleus. Two protons and two neutrons. So the original nucleus, let's take this one here, this is a nucleus of plutonium-240. Because it's released two protons and two neutrons, the atomic number, or the proton number of the atom, will go down by 2. All right, so in this case it will go down from 94 to 92, and the mass number, or the nucleon number, will go down by 4 because you've released 4 altogether. So in this case it will go down from 240 to 236. Now, because the proton number has changed, the actual element itself has changed, and the place of that atom will change in the periodic table because it's actually become something else, a new type of atom because it's lost protons. Okay, so that's the nature of alpha decay, and that's what's happening there. So let's have a look at some of the properties of these alpha particles themselves. The charge is +2 because you have 2 protons. Obviously the neutrons are neutral. The relative mass in terms of one proton is 4. Sorry, that shouldn't really be +4, just 4. They've got a relative mass of 4 because you've got 4 nucleons there. The relative speed compared to the others is quite slow. Alpha particles travel reasonably slowly. I mean, we're still talking about 10 to the 5 meters per second, so not slow by our standards, but slow in terms of, you know, when you're looking at it relative to the others. Penetration means how far into materials it can get before it's absorbed and before all its energy is gone. And for alpha particles, the penetration is quite low. They're not very penetrating, they're absorbed quite quickly by materials. Range in air is probably just a few centimeters. All right, so if you had an alpha source, it would probably not go much further than 10 centimeters, the alpha particles, before they were absorbed by the air, the molecules of the air. Its ionizing power, however, is very high. It can do a lot of damage to material or to atoms on its way through them. So even though it doesn't get very far into them, it does ionize them very highly along the way. And there's definitely a correlation between these two. Obviously, as it ionizes, it's going to lose energy as it hits each, electron or whatever as it's going through the material. For each ionization, it will lose quite a lot of energy, kinetic energy we're talking about, and therefore it actually won't get very far until it's stopped. So those are some of the basic properties of the alpha particles. Here's a little bit more detail on the changes to the atomic and the mass numbers of the isotope as alpha decay is occurring. So this is a general formula here that you can use. So Z is the proton number or the atomic number, and A is the mass or nucleon number. So with the emission of an alpha particle, which is sometimes written as He 42, like that, because it's equivalent to a helium nucleus, we have the atomic number reducing by 2 and the mass number reducing by 4. And there's a couple of examples down there for radium and for uranium in their alpha decays, and these are real alpha emitters here. Okay, now beta decay. At GCSE you learned that beta decay was just beta decay, but actually there are 2 types of beta decay. There's what we call beta minus and beta plus. Now they're essentially the opposite processes, and that's why they're denoted by the minus and the plus signs. And we're going to have a look at each one in turns and see what that means. Okay, now the 4th force that we looked at in the nucleus is called the weak nuclear force. Now, as we said, the weak nuclear force is the one that's responsible for beta decay. Now, the weak nuclear force has the unique property or the unique ability to change the flavor of the quarks within a hadron. And in our case, within protons and neutrons, because they're obviously the nucleons, which is what we're talking about. So it can actually change their structure by changing the flavor or the type of the quarks that are in the nucleon. So specifically, what we're talking about is that if you have an up quark, it can mutate into a down quark. It can actually change its flavor spontaneously via the weak interaction. So we're going to have a look at what change that will actually cause to the particle itself. So here we have a particle with 1 up and 2 down quarks. So this is actually a neutron. And what we're going to say is that this down quark here is going to change its flavor and become an up quark. So this down will change into an up. Now, what change is that going to have to the actual particle itself? Well, obviously this is a neutron because it's up, down, down. This will actually turn it into a particle which has up, up, down. And as you may remember, that particle is the proton. So the neutron, one of the neutrons within the nucleus, will turn into a proton. Now this is actually a reversible, well, not really reversible, but the opposite can also happen. Via the weak nuclear force, an up quark can actually turn into a down quark as well. So you can also get protons turning into neutrons spontaneously within the nucleus. Okay, so what does this mean then? Well, let's take the one where the neutron turns into a proton, for example. If the neutron turns into a proton, the neutron was neutrally charged and the proton is positively charged. So effectively what you've done is you've created a new positive charge within the nucleus where before you had none. Or you know, you've got an extra one anyway. I mean, there were charges within the nucleus, but not from this particular neutron. Now, nature says, hang on a minute, I'm not going to allow you to do that. One of my basic conservation laws is that the charge must remain the same. And so because you've created a new positive charge, what also has to happen is a negative charge must be also created from the excess energy within the nucleus. Now, that negative charge comes away from the nucleus in the form of an electron. And the electron is what we call the beta particle. Now, all the beta particle is an electron. And it's emitted from the nucleus because it's formed when the neutron turns into a proton. And the reason it's formed is to balance out the charge. So the excess charge and the excess energy is released as a beta particle, okay, which is an electron. Another particle is actually also emitted, and that's what we call an antineutrino. Now, we learned about neutrinos when we were looking at hadrons and leptons, and a neutrino is a lepton, so a very tiny neutral particle. And the neutrino is also emitted in order to conserve things like angular momentum within the nucleus. It's an antimatter particle as well. It's an antimatter pair to a neutron, sorry, to a neutrino. But that's a sort of subtle point that we don't really need to go into in this video. So a beta minus equation would look something like this. Here's an isotope of radium. Now it has an atomic number of 88 and a nucleon number of 228. With the emission of this electron, right, which is given the atomic number of -1, which sounds a bit strange because this is effectively the number of protons, but in this case we need to view it as the charge number really. So it has an atomic number of -1 because it's negatively charged, and a mass number of 0 because it contains no protons or neutrons, it's just an electron. So with the emission of that, what happens to the atomic number is that it will actually go up by 1. Whereas in the case of alpha particles, it went down by 2. Here, we've got it going up by 1, effectively because a neutron has turned into a proton. And mathematically, obviously, the numbers need to balance on either side of the equation. So 88 is equal to 89 plus -1. So that's how that number is arrived at there. Because there are no protons or neutrons lost across this, this reaction, the mass number remains the same. So it's 228 to begin with, and it's 228 in the isotope that we end up with as well, because none have actually been lost from the atom. The neutrino has got numbers of 0, 0 as well, just for completeness there. It's a tiny little particle, no protons or neutrons, no charge. Okay, so the charge on beta minus particles, because they're electrons, is -1, or minus E if you like, because it's an electron, so it's got an electron charge. The relative mass is very small, about 1/2000th that of, sorry, let me just rub that out so it's a bit clearer. About 1/2000th of that of a proton. Its speed is moderate, let's say medium. We're talking about around about 10 to the 6 to 10 to the 7 meters per second. Penetration again is medium. It's absorbed by materials like aluminium, thick aluminium. Range in air is a few meters, so a beta particle will travel a few meters through air before it's absorbed, And again, its ionizing power is medium. It will ionize particles along its track, but nowhere near as strongly as an alpha particle will. Okay, so those are the properties of beta minus particles. Beta plus decay is slightly more unusual, but there are quite a few naturally occurring, well, there are some naturally occurring beta plus emitters. Now this is, as I said, the opposite of a beta minus decay. So here what we've got is, rather than a neutron turning into a proton, we've got a proton turning into a neutron. So one of the up quarks will actually turn into a down quark in this particular instance here. Now, because you've got a proton with charge +1 turning into a neutron with charge 0, you have lost a positive charge. Again, nature will not allow this. Conservation of charge is extremely important. So that positive charge that's been lost has to reappear somewhere. And it reappears in the form of an anti-electron, which is otherwise known as a positron. Now, positron is the antimatter particle of an electron. It has exactly the same properties, except it is positively charged. There we are, positron. Okay, so that's where the excess energy comes out, and that's where the positive charge comes out as a positively charged electron, otherwise known as a positron. And in this case, a normal matter neutrino is emitted as well, for the same reasons as the antineutrino was emitted during beta decay. So if we have a look at a beta plus equation, we have here's your positron, all right? Now this one has a proton number of +1, so it's got a charge of +1 because it's positive, and a mass number of 0. Again, the neutrino here has 0, 0 in terms of mass and atomic numbers. So what happens here is, again, just the opposite. The proton number or the atomic number of the isotope that you started with reduces by 1 because one of its protons has turned into a neutron. And the excess charge, the 1 that you've lost, appears over here with the positron. The mass number again stays the same because you haven't actually lost any protons or neutrons from that particular nucleus. Okay, the properties of beta plus particles are almost exactly the same. Let's just go back to that one. The properties of beta, if this said beta plus here, the only thing that would be different is the charge. So the charge of a beta plus particle is +1, whereas beta minus is obviously -1. Okay. Now gamma decay is the emission of a photon of electromagnetic energy in the gamma spectrum. That's it. Just like electrons have energy levels as they're orbiting around the nucleus, so too do nuclei have energy levels. And effectively, when a gamma photon is emitted from a radioactive nucleus, the nucleus is simply moving from a higher energy state or a higher energy level down to a lower one or a less excited state. So obviously that's quite analogous to electron shells. So the point about gamma that I want to raise here is that no structural changes occur at all. Quite often, a gamma emission will happen immediately after an alpha emission. So you will see alpha emitters, which aren't pure alpha emitters. They'll emit an alpha particle, and after which the nucleus will be in an excited state, and then it will drop down to a lower state by the immediate emission of a gamma ray. Okay, so that's easy. Gamma decay is quite easy to deal with. In terms of the properties of gamma photons, the charge is 0, the mass is 0, right? So because they're just energy. The speed, they travel at the speed of light, which is normally given the symbol little c. The penetration is very high. Okay, so they're very good at penetrating materials. They are partially absorbed by lead or thick concrete, but even then, you know, it's only attenuated by those materials rather than completely absorbed. The range in air is technically infinite, so they can travel quite a long way through the air, through you know, materials in general, and their ionizing power is very low. It's not 0. Okay, they do ionize materials. All three of these, alpha, beta, and gamma, are all ionizing radiation. So they do have that capability, but because they have such high penetration and effectively they're just photons of energy rather than big particles, they don't cause much ionization at all. Okay, so those are the properties of the three types of emission. Now, some types of emission happen with different size nuclei is the best way to put it, or different ratios of protons to neutrons. And this is a graph of neutron number against proton number. And you can see there's like a dark red line coming up here. That is the line which has a 1-to-1 ratio of neutrons to protons. Now, down the bottom end of the periodic table with the lighter elements, a lot of the isotopes are around that 1-to-1 ratio, but as they increase, as you go up the periodic table and you get heavier and heavier elements, you tend to get a greater number of neutrons to the number of protons in any particular isotope. And that ratio is really important in determining which type of emission you're going to get. So if you have a large number of neutrons compared to protons, you tend to get beta emitters. Whereas if you have a smaller number of neutrons compared to protons, you tend to get beta plus emitters. And there aren't as many natural beta plus emitters, there aren't as many natural isotopes on this side than there are on this side, but those are the ones that tend to be there. Alpha emitters tend to be larger nuclei, very large nuclei at the top end of the periodic table. Again, with a lower, particularly in this section, a lower number of neutrons relative to others compared to protons. Okay, so that's that, and those are some of the properties of alpha, beta, and gamma. Thank you very much.